1/2, right? Are you guys cool with that?
Yes.
And again, this is why this works. You never have to do this. Could I then, if I wanted to, couldn't I take that 1/2 power back out? Didn't somebody like distribute it across? Couldn't I do this?
Yes.
You stop right there. Isn't that the same thing? This would be 1/2 to the 2 and 1/2 to the 7, so they are the same thing. And don't I now have 2 times 7? Inside of a square root. So as long as it's the same root, that power can come out and you can just do the things on the inside together. Does that make sense? That's why this works. So thank God it is exactly what your gut tells you it should be. You're like, thank God, gut, for once math agrees with us. 14 to the 1/2, which is, that's square root of 14 we got. So please, dear God, don't do this. Just do this. As long as it's the same root. So what do you think about the situation in Littleview? No. What do you think about square root of, let me see if you guys, okay. Square root of 3 times square root of 3. We'll keep it nice. Square root of 9, which is, so think about why that makes sense. Now one thing is they're both the same root, so I can multiply them together. I happen to end up with something I can simplify. Why does that just totally make sense? Because square root of 3 is half of 3, right? 3 to the 1/2. And if I multiply it by its missing half, oh, I made a whole 3 out of it, right? Does that make sense? So I can kind of do a shortcut then. What's square root of 7 times square root of 7? 7. Because it would be square root of 49, which is freaking 7 anyway.
Yes.
Because, see that?
Yeah.
So what about cube root of 2 times cube root of 2 times cube root of 2?
It's 2.
Yeah, so if you wanted to, you could say cube root of 8, which is 2.
Yeah.
But really, that's 1/3 of 2, 1/3 of 2, 1/3 of 2, and it makes a whole 2 at the end.
Yeah.
So you can look at it either way you want to. You can always multiply them because of the same root, and then just simplify, or you can say, oh crap, that's a whole freaking 2. 3 pieces of 1/3 of 2 makes a whole 2. Okay, maybe.
We got this.
Yeah, not too bad, right? All right, let me throw you something here. What's the square root of 7 times the cube root of 4? I'm glad you're having trouble because you can't do that.
No.
Why can't you do that?
Because they are
Different roots.
different.
Beautiful. So some of you guys are like,
Different roots.
it's just something weird here. You want me to say different roots with the 3? Yeah, so they're different roots. I can't do shit. Right? That's it. That's all it is. I can't do anything with it because they're different
Leave it like
roots.
this.
They have to be the same root for me to put them together. I can't simplify either one of these. And I can't put them together, so that's it. Cool. All right. So that seems simple, which is always makes students a little worried for some reason. It is simple. What do you guys think about this? They're both the same roots. I'm allowed to put together the insides. I could actually even look at it like this.
Square root of 25.
Make one big root,
Square root of 25.
which is 5. I love it. Right? They're both the same roots. I'm allowed to divide them. So I get 25 on the inside, and the square root of 25 is 5. So some of these you will be able to simplify at the end. Some of them you won't be able to simplify at the end. Right? You just leave it alone.
How did you get 25 out of 50 over 2?
What is 50 divided by 2?
Okay, so you could do it that way, you're just dividing.
Yeah, that's all it wants me to do, divide. And I'm allowed to divide these numbers because the roots involved are the same. In fact, what is 50 divided by 2 by itself?
25.
Because they both have the same root. No root. So we've already used this property that we can only divide numbers that have the same root. We've already used it. It just didn't have a root. Now, if they have a square root, the other one better have a square root. One's a cube root, the other one better freaking have a cube root. The roots have to be the same. We've actually kind of known it. We just didn't have other roots to compare it to. Okay. Let's see now. Here's something interesting. What if I have just the square root of 50 sitting there by itself? You might say, well, I don't know what the hell the square root of 50 is.
25 to the power 2.
Careful. 25 times 2. Real quick though, isn't the square root of 50, isn't that just barely over what number? Because 50 is just barely over 49. So square root of 50 is just something like 7 point something. Alright, Alright, cool. So you can estimate roots. But here's the trick. 50, like you guys are telling me, is 25 times 2.
5 times 5 times 2.
And can't I do this property where I put them together, can't I do it opposite? Isn't it the same thing as 25 breaking it up?
Yeah.
Because we've been doing this way. Well, math can always go both ways. So there is.
So.
The square root of 25 is 5. And the square root of 2, I don't know.
That's
So whenever you have a radical that's not like 49, square root of 49 is 7, that's direct. Square root of 50 I can't do, but I can do a piece of it. So I break it up into something I can do and something I can't. I do the part I can, I don't do the part that I can't. That makes sense, right? And this is really exactly like, what if I had 18 divided by, oh, let's see what I want to say. 10.
9 over 5.
Right? And why is that? Because you break up 18 like 2 times 9
Yeah.
Times
2
5.
times
5.
5.
and 2 times 5. And then you do the part that you can, and you don't do the part that you can't.
Yeah.
Yes.
So it's a lot like that. 18 I can't divide it by 10 and get a nice whole number, can I? But I can certainly break it up. I can break it up so that a part of it I can do and a part of it I can't. Is that cool? Do you guys see that?
Yeah.
Same kind of thing. Same kind of thing. Here, you guys try this one. Oh, let's see. Let's see. Ooh, that's really hard. Put something up there, Jeff. Now here it's really important that you know your square rootable numbers or your cube rootable numbers, right? You can't do it directly, I agree with you, but you can probably do it like we did here. Oh, square root or radical. If it's got a little 3, it'd be a cube root. Yeah. You see, it's a radical symbol. Yeah. I like it. So this first one,
3.
you can't do the square root of 27 directly.
No.
You know it's a little more than 5, because 27 is a little more than 25.
9 by 3.
Exactly. 27 is 9 times 3.
Times 3.
You break those up.
Yeah.
Yeah.
Square root of 9 I can do. Square root of 3 I can't.
You can?
I can't do the square root of 3. If you can, you're better than me. So is that, I mean, it's almost too simple. You do the part you can, you don't do the part you can't. The whole trick, though, is to break it up correctly. 24 is 4 times 6, sure. But is that a smart way to break it up?
No.
What's a good number for cube
8.
roots?
8.
8, right? And we know that from our factoring cubes. We know some of these numbers already. So this is cube root of 8 times 3. I can break that up.
2.
Cube root of 8 is 2. Cube root of 3 is, I don't know. So I call this procedure simplifying radicals. Or even I call it reducing the radical, right? Because it is a lot like reducing a fraction.
So the cube goes along to the right, by the way.
Oh, hell yeah. If you lose that 3 here, you've changed the radical from what it used to be. And you're not allowed to do that. You gotta be, I'm glad you said that, because a huge mistake is people start off with all these 4th roots, and the next line they're all square roots. And then the work after that is based on a square root. It's not a square root, it's a 4th root. You can't do as much, right? So you gotta, don't leave that poor little root out. He's gotta come the whole way.
Yeah.
Cool. So now we've almost, we've come kind of full circle here. Let me go back to the very first thing we did, combining like square root of 5 plus square root of 5 is 2 square root of 5. What do we do when they're not like terms? Is there something we could possibly do?
Make them like terms.
Try to make them like terms. So let me start off nice. By the way, I can't remember if I said this or not. I'm sure you guys have noticed that I'm really bad about this, but it's just because these are all over the place. This is actually 7-3. And I don't like the fact that they put that in 7.3, because it makes a lot more sense if you talk about putting these together first and then saying I can tear them apart the same way. So their 7.5 is multiplying, is doing it this way, and their 7.3 is doing this, is breaking it up. Okay, so we've actually already done 7.5, most of 7.5 already, which is just starting here and multiplying them together.
So would you suggest doing the 7.4 homework before doing 7.3?
Not necessarily.
About
As long as you understand all this, you got it, right? It's just I want to explain it in this order. Now I've completely, oh yeah, that's right. So back to 7.
3.
I gotta keep myself straight. No, 7.4. Just remind us what this was about. 2 square root of 10 minus 5 square root of 10, what would that be? Good, -3 of those. Cool. That's nice. They already started off as like terms, bam. So what about this? Square root of 40 minus square root of 250.
Can't do it.
Not yet.
Break it into pieces.
Break it into pieces, I love it. So now we have a way to try to make them the same. If they both simplify so that they both have the same, like this is 10 and 10, some of you guys might realize something based on what I just said. How would you break 40 up?
10 and 4.
4 times 10, because I can take the square root of 4, right?
yes.
I know 40 is 8 times 5, but that way sucks, because neither 8 or 5 are good for square roots, right? So you always want to break it up. So one of them is good with its root, and the other one isn't.
Yeah.
Of course, this one would be
25 by 10.
cool.
Yes.
So here I get square root of 40 is square root of 4 times square root of 10, right? That's what we just figured out. 250 is square root of 25 times square root of 10, so that's 250. Square root of 4 is 2. Square root of 25 is 5. And now it's the same stupid problem, right? Now they are like terms. They were not like terms here, but now they are. Cool. And it's kind of like, it's exactly like, let's see if I can do this quickly here. Yeah, Jeff. It's a lot like this problem, believe it or not. Because are they like terms right now?
No.
But instead of multiplying that, what can I do here?
Okay, we can,
Reduce.
yeah, can see.
1236 reduces to,
1/3.
so 1/3 minus 1/3 is 0. So this is simplifying a radical, or I call it reducing a radical, because it's very much like reducing a fraction. They're not like terms at the beginning, but if I reduce them, now I have like terms. Will it always be that way? Of course not. But most of yours should be, because that's the whole point, right? You're trying to make them like terms by reducing each radical. Let's do one more together, and then I'll give you guys a few to try. Come on, you can do it, John. Maybe. Let's do this one together. Which one is easier to handle?
8 by 5.
Yeah, the 40 is. I'll do that first, and then I'll get a clue as to what the hell to do with that. Let's see if you guys see what I mean. 40 is, of course,
8 by 5.
8 times 5. Well, we did do it there, but it's related to that in a way. But now I want the 8 to 5, because the cube root plays well with the 8.
Yeah.
Now, I want to do this wrong, because there's a 4 out here, right?
Yeah.
So if I rewrite it, 4 times cube root of 8 times cube root of 5, right? Just breaking up the 40 into 8 and 5. Is that cool? Minus, now I kind of know what to do with this. What do you think I want to have? What number do I want to try to put into that?
8.
No.
5. Why does that make sense? Because the only way these are going to be like terms is if there's a 5 left in here. And sure enough, 5 times what?
Sorry.
Math needs sound effects.
Yes, 5 times that sum. No, 5 times
5
what?
times.
27.
27. Do you guys kind of see what I'm saying?
Whoa.